Assalamualaikum warahmatullahi wabarakatuh. For part number 4, we will learn about the method to increase the efficiency of the Rankine cycle. So previously we already learned about the ideal Rankine cycle and also actual Rankine cycle. When we consider actual Rankine cycle, if you compare in terms of efficiency, compare with the ideal Rankine cycle, the efficiency of the actual Rankine cycle will be less than the efficiency of the ideal Rankine cycle. So now what we want to know, what are the methods can be used to increase the efficiency of the Rankine cycle. So in this part we will learn the general methods to increase the efficiency of the Rankine cycle. Okay, method to increase the efficiency of the Rankine cycle. So the figure shows the basic schematic diagram for the steam power plant and also the ideal TS diagram for the Rankine cycle. Okay, so in order to know the method how to increase efficiency, so we need to refer to the general equation for thermal efficiency, where thermal efficiency equal to W net divided by Q in. Okay, so if you refer to the TS diagram, the area enclosed by the Rankine cycle will represent the value of W net, where W net equal to W out minus W in. Okay, so if we can increase W net a value, so we can increase the thermal efficiency of the Rankine cycle, which means if we refer to the TS diagram, if we can increase the area of the area that enclosed by the Rankine cycle, we can increase the value of W net, and then we can increase thermal efficiency. And also we can reduce the value of Q in. Okay, so the value of Q in actually in actual condition represent the amount of fuel that used for the heat addition process in the boiler. Okay, so if we can increase W net, the thermal efficiency also will increase, or we can decrease or reduce the value of Q in, the thermal efficiency for the Rankine cycle also will increase. Okay, so there are two approaches that can be used to increase the efficiency of the Rankine cycle. First, we can make some modification at the condenser, where we need to decrease the value of T average. TAV means T average at heat rejection process, which means we need to reduce the value of temperature T1 or the temperature of T4. Okay, so T average here means, for example, if we have two temperature, for example T1 and also T4, T1 plus T4 divided by 2, so we will get T average. Okay, so if we can reduce one of this temperature, the average temperature T average at the condenser will reduce. Okay, so when the temperature during heat rejection reduce, the value of W net will increase. Okay, the second approach is at the boiler. So we need to make some modification so that the value of T average during heat addition process will increase. So this temperature will involve the temperature of T2 and also T3. So if we can increase the temperature of T2 or the temperature of T3, we can increase the value of T average. Thus, the value of W net also will increase if we use this approach. Okay. Okay, so in terms of method, under what we call under the method where we make some modification at the condenser, where we decrease the value of T average during heat rejection process, the first method we can do modification in terms of lowering the condenser pressure. When the pressure of the condenser reduce, T low average, which means the temperature for the condenser also will decrease. Okay, the second method under the what I call the modification of the boiler, where we increase the value of T average during heat addition process, we have the second method that we call superheating the steam. Okay, where we will increase the temperature of T3. When we increase temperature of T3, the value of T high average, where T high refer to the temperature during the heat addition process, will increase. And the third method, still under the modification at the boiler, by increasing the value of T average during heat addition process. The third method is where we need to fix the value of T3, and then we increase the value of boiler pressure. So by using this approach or this method, the value of T high average during heat addition process will increase. Thus, the value of W net also will increase for the Rankine cycle. Okay, method number 1, the method to increase the efficiency of the Rankine cycle. So in order to increase the thermal efficiency of the Rankine cycle, one of the method is by lowering the condenser pressure, where if we can reduce the condenser pressure, the pressure during the condensing process, we can reduce the average low temperature during the condensing process. So the low temperature refer to the temperature during the condensing process in the condenser, or during the heat rejection process in the condenser. Okay, so if you look at the TS diagram, so the TS diagram shows the basic ideal Rankine cycle that represented by red color line cycle. So if you reduce the pressure of the condenser during the heat rejection process, we will have new additional what I call the area that represent the value of the increase of W net for the method number 1. And we will have new state for state number 1, state number 2, and also state number 4 that represent by 1 prime, 2 prime, and also 4 prime respectively. Okay, so as we mentioned before, if we can increase the value of W net, the thermal efficiency also will increase. So by implement the what I call the method number 1, where we reduce the pressure of the condenser, so we can increase the value of W net. Okay, however, in terms of characteristic, when we lowering the condenser pressure, so we will have lower value of saturated temperature, especially during the heat rejection process in the condenser. So this saturated temperature refer to the temperature of I call the saturated temperature for the new constant pressure line, when we reduce the pressure of during heat rejection process. So the steam temperature also reduced. So this steam temperature actually refer to the state number 4 or state number 4 prime. So if you compare in terms of steam temperature, which is the outlet condition at the turbine, so state number 4, if you compare with state number 4 prime, state number 4 prime in terms of temperature will be lower compared to state number 4. And then during the process, when we lowering the condenser pressure, so we also have the increase of Q in. However, this increase is very small, and this process, the increase of Q in actually refer to the process involved with state number 2 prime and also state number 2, as shown in the TS diagram. Okay, the next characteristic for this method, the quality of steam will reduce, which is referred to state number 4 and also state number 4 prime. So after we reduce the condenser pressure, so in terms of X, the quantity of steam at state number 4 prime will be decreased, and this will cause the increase of moisture content. So we need to avoid the increase of moisture content, because this will damage the surface of turbine blade. So these are the characteristics if we lowering the condenser pressure for the Rankine cycle. Okay, so overall we will have the increase of W net, and then the thermal efficiency for the cycle will be increased. However, for this method we have limitations, where when we lowering the condenser pressure, the air leakage into the condenser might be happen. For the effective heat transfer process, the the condenser pressure must be greater than the saturated pressure for the cooling medium. So cooling medium here, if you look at the schematic diagram as shown in the slide, is cooling medium that come from the cooling tower, where this cooling medium will use to absorb heat from the condenser for the heat rejection process. So in this schematic diagram shows the inlet temperature of 15 degrees Celsius, outlet temperature of the cooling medium after absorb heat from the condenser, let's say around 25 degrees Celsius. And for the effective pressure, the delta T normally at 10 degrees Celsius. And for this example, the saturated pressure for the cooling medium is around 3.2 kilopascal. So in order to lowering the condenser pressure, so we need to make sure that the value of condenser pressure must be greater than the saturated pressure of the cooling medium. In this case, must be greater than 3.2 kilopascal. Although we want to lowering the pressure, so we need to make sure that the value of pressure that we reduce still must be greater than 3.2 kilopascal. If not, the condenser will have air leakage during the heat rejection process. Okay, method number 2. In order to increase the Rankine cycle efficiency, we can use this method where we superheating the steam in the boiler, where our focus actually want to increase the temperature of T3, the temperature at the outlet of the boiler, and also the temperature at the inlet of the turbine. So if we can increase this temperature, the average high temperature will increase, where the high temperature actually refer to the temperature during heat addition process in the boiler, shown in the TS diagram. So our concentration here now, we want to increase the value of T average during heat addition process by increasing the value of T3, so that we can have the higher value of T average during heat addition process in the boiler. Okay, so if we look at the TS diagram, so we want to know what is the effect if we increase the temperature of T3. Okay, now if we increase temperature of T3, the increase in W net, so we will have additional area that represent by red color area. So this area represent the increase of W net, okay, after we increase the temperature of T3. Okay, by using this method, T average during heat addition process will increase. So now we will have new state for state number 3 and also state number 4, which is represented by state 3 prime and also state 4 prime respectively. Okay, now in terms of characteristics, if we implement the second method by superheating the steam, obviously the W net will increase as shown in the TS diagram, and the quality of steam also will increase, so we will have less amount of moisture content during the expansion process in the turbine. This X value represent the X value or quality of the steam at state number 4 prime. So if you compare state number 4 and also state number 4 prime, state number 4 prime in terms of quality will have higher value of quality, steam quality, compared to state number 4, and less moisture content will obtain. So this condition is good for the turbine. However, we have some limitation if you want to use the second method, the method that we need to superheating the steam. So the limitation is the temperature for T3 prime. So we cannot just simply increase the value of T3 prime at any value. So the T3 prime, if you want to increase, we need to make sure that the temperature must be lower than the maximum temperature that allowed for the a turbine blade material. Okay, so the turbine blade material will have a certain limit, so we cannot cannot exceed the limit, because if we exceed the limit, maybe we will change the structure of the blade material, so the blade material probably will melt or will damage. So the typical value of the maximum temperature for the turbine blade is around 620 degrees Celsius. Okay, so this is the maximum value. So in actual condition, if you want to increase the temperature of T3 or T3 prime, you need to make sure that the temperature must be lower than 620 degrees Celsius. Method number 3, to increase the efficiency of the Rankine cycle, we also can increase the boiler pressure. Okay. However, for this condition, because we already know that for method number 2, the value of T3 cannot exceed a certain value, which is referred to the maximum temperature for the turbine blade. So now, before we increase the boiler pressure, we need to fix the temperature of T3, the temperature at the outlet of the boiler or the temperature at the inlet of the turbine. And then we increase the boiler pressure, the pressure during heat addition process. So as a result, the value of average high temperature will increase. Okay, so if you look at the TS diagram, what is the effect if we increasing the boiler pressure and also fix the value of T3? So now we fix the value of T3 and then we increase the pressure of the boiler. Okay, so you can see that by using this method, we will have the increase in W net value that represented by the red color area in the TS diagram. However, at the same time, we will have the decrease in W net as shown by the green color area in the TS diagram. Okay, so we have both. By using this method, we have both. First, the increase in W net, and the second one, we also in the same time also will have the decrease in W net. So for this method, we will have new state for state number 2, state number 3, and also state number 4, which is represented by state 2 prime, state 3 prime, and also state 4 prime respectively. Okay, so now if you look the TS diagram in terms of characteristic, if we use this method, the saturated temperature will increase during heat addition process. The value of Q in will reduce. So this is good, because if we can increase W net, the thermal efficiency also will increase. Or if you can reduce the value of Q in, the thermal efficiency also will increase. Okay, so now by implementing the increasing the boiler pressure, the value of Q in will reduce. So this is good. This is good for the Rankine cycle efficiency. However, at the same time, the value of Q out also decrease. Okay, so we have the reduction of Q in value that represented by the process between state number 2 prime and also state number 3 prime. And also we have the decrease of Q out, or the reduction of Q out value that represented by state number 4 prime to state number 1. Okay, and the other characteristics, the value of steam quality will decrease, that represented by state number 4 prime. If you compare with state number 4, state number 4 prime in terms of X value will have lower value of X compared to state number 4, which means we will have more moisture content during expansion process in the turbine. So in order to compensate in terms of moisture content, so if you want to reduce the moisture content and still want to increase the boiler pressure by using the method number 3, so we can add to the system a specific process that we call reheating the steam process. Okay, later on we will learn about this process in the next part of this chapter. In terms of limitation for this method, the limitation is we need to make sure that the value of W net increase, that represented by a red color area, must be greater than the W net decrease, that represented by green color area. Okay, then we will get a higher value of W net total. If not, we will have lower value of W net. Okay, so that's the limitation for this method. We need to make sure that the W net increase must be greater than W net decrease. Okay, as the summary, in terms of the method to increase the efficiency of the ranking cycle, we have three general methods in order to increase the efficiency of the ranking cycle. First method, by lowering the condenser pressure. If we can reduce the pressure at the condenser during heat rejection process, the average low temperature will reduce, so we will increase the value of W net for the Rankine cycle, as shown in the TS diagram. The second method, we can use superheating the steam method, where we increase the value of T3, the outlet temperature of the boiler, or the inlet condition of the turbine, which is referred to state number 3. By using this method, we can increase the average high temperature during heat addition process at the boiler. So by implementing the second method, we will increase the value of W net. The third method, by increasing the boiler pressure, but first we need to fix the value of T3. Okay, and also we will have higher value of average high temperature during heat addition process. Okay, as shown by the TS diagram. However, we need to make sure that the value of W net increase by implementing this method must be greater than the value of W net decrease after we implementing the methods. Okay, so these are the general method on how to increase the efficiency of the Rankine cycle. Example 4.3. Consider a steam power plant operating on the ideal Rankine cycle. Steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. Determine A, the thermal efficiency of this power plant. B, the thermal efficiency if steam is superheated to 600 degrees Celsius instead of 350 degrees Celsius. And C, the thermal efficiency if the boiler pressure is raised to 50 megapascal while turbine is maintained at 600 degrees Celsius. Okay, so if you look at the question, the data given, the pressure of 3 megapascal and also temperature of 350 degrees Celsius, actually they represent the condition at the inlet of the turbine. So if we consider the ideal Rankine cycle, so this information actually is for state number 3. And then the pressure of 10 kilopascal is the pressure at the condenser during heat rejection process, which means because during the heat rejection process the pressure is constant for the ideal Rankine cycle, so the value of P4 and also P1 will be equal to 10 kilopascal. Then you need to determine the thermal efficiency for different cases. So in this question you need to solve 3 cases of the 3 conditions of the Rankine cycle, where you need to determine the thermal efficiency. Okay. Okay, now determine the thermal efficiency of this power plant. So we just draw a schematic diagram for the ideal Rankine cycle. So we have 4 main components: pump, boiler, turbine, and also condenser. So we need to know that we will have W in at the pump, Q in at the boiler, W out at the turbine, and also Q out at the condenser. So for the ideal case, so we will have 4 states involved. We need to put whatever data given in the question into the schematic diagram. So we have state number 3 at 3 megapascal, in terms of temperature 350 degrees Celsius. Due to what we call the constant pressure during heat addition process, the value of P2 also equal to 3 megapascal. So in the question also give you the pressure of condenser. So now we will know that the P4 value will be equal to P1 value equal to 10 kilopascal. So that's the information that we have to answer the question. So, and then other than the schematic diagram, we also need to draw or sketch the TS diagram and plot the what I call the information given to increase our understanding about the problem. So we have 4 states involved, and because the process is ideal Rankine cycle, so the compression process will be isentropic. Expansion process in the turbine also isentropic. Okay, so we have 2 constant pressure line. We just draw 2 constant pressure line of 10 kilopascal and also constant pressure line of 3 megapascal. And the state number 3 is at 350 degrees Celsius. In terms of state, for the ideal Rankine cycle, we know that state number 1 will be at saturated liquid, state number 2 will be at compressed liquid, and the process will be isentropic for the compression in the pump. So we will have constant pressure during heat addition process, and the state for state number 3 is superheated. However, for state number 4, we need to confirm the state, where we need to check first the state, because the state for number 4 might be in saturated mixture or might be in superheated vapor. So we need to check first for state number 4. The others, because we consider the ideal Rankine cycle, we already know the state, okay, as I mentioned before. Okay, so now we need to determine the thermal efficiency for this case. Okay, so keep in mind, so when you want to solve the problem involved with Rankine cycle, so make sure that it is better to determine the important parameters such as enthalpy, temperature and so on for each state, state number 1 until state number 4, because later on we need to use this value to determine the thermal efficiency and so on. If let's say you doesn't know how to solve the problem, just determine the important value for every state, state number 1 until state number 4. So most of the mark in terms of solution you already obtain around 50%, 60%. You already obtain the mark in terms of solution. Okay, so to determine the thermal efficiency, we can use this formula where thermal efficiency equal to mu Th equal to W net divided by Q in, or you can use the second equation where thermal efficiency equal to 1 minus Q out divided by Q in. And W net equal to Q in minus Q out equal to W out minus W in. So in terms of data given, so P2 equal to P3 equal to 3 megapascal, T3 equal to 350 degrees Celsius, P1 equal to P4 equal to 10 kilopascal. Okay, now we need to find the important value in terms of especially the enthalpy value for state number 1. For state number 1, the data given P1 equal to 10 kilopascal. So now for the water table, at least we need to have 2 data or 2 information. So now, because the cycle is ideal Rankine cycle, so for state number 1 we already have 2 information. First, the pressure P1 equal to 10 kilopascal. The second one, we know that the phase for state number 1 is saturated liquid. Thus, in order to determine the important value or important parameter for state number 1, we need to use the saturated water table based on pressure, because the value of pressure is given in the question. Okay, so at pressure equal to 10 kilopascal, so you can determine the value of H1, where H1 equal to HF at 10 kilopascal equal to 191.83 kilojoule per kg. And also you can use you can obtain the value of V1 equal to VF at 10 kilopascal equal to 0.001010 meter cubic per kg. So why we need to determine V1? So later on maybe we can manipulate this value by using the equation for the W in, where W in equal to V1 multiplied by P2 minus P1 in order to determine the important parameter for state number 2, especially the value of H2. Okay, now for state number 2, state number 1 we already done. State number 2, the process the state will involve with the isentropic process in the pump, where we have the compression process from state number 1 to state number 2. So we know that the pressure given for P2 equal to 3 megapascal, and because the process is isentropic, S2 equal to S1. And we know that after the compression process, the water condition will be in compressed liquid. However, data is not available for 3 megapascal in compressed liquid table, so we cannot use the table, the compressed liquid table. So we need to use the formula that we have learned, where W pump in or W in equal to V1 multiplied by P2 minus P1 equal to H2 minus H1. So by using this equation, we can determine the value of H2. Okay, so W in, if we substitute the value of V1 P2 minus P1, W in will be equal to 3.02 kilojoule per kg. Okay, and due to the value of H1, V1, P1 we already determined for state number 1, and P2 already given, we just rearrange the equation so we can obtain the value of H2. H2 equal to 194.85 kilojoule per kg. So that's how we calculate the value of H2, although we don't have any data for the compressed liquid table. Okay, for state number 3, the inlet condition of the turbine, where P3 already given, which is equal to 3 megapascal, T3 also already given in the question, which is equal to 350 degrees Celsius. So we already have two data, and actually we already know the phase is superheated vapor. However, if you, let's say we want to check, want to confirm about the phase, we can use saturated water table, because sometimes the problem will involve at least the state number 3 will be at saturated vapor. Okay, so let's say you want to check the phase, so you need to use saturated water table based on pressure table. So refer to the pressure value P3. So P3 at 3 megapascal, determine the T saturated or saturated temperature at 3 megapascal. So we have T saturated at 3 megapascal equal to 233.9 degrees Celsius, and then compare this value, saturated temperature at 3 megapascal, with the value of T3, and the value of T3 actually is greater than the saturated temperature at 3 megapascal, so the phase confirms superheated vapor. And now, in order to determine the enthalpy value and also the entropy value and so on, we need to use the superheated vapor table or superheated water table. Okay, because we already know the pressure and also the temperature, so easily we can determine directly the value of H and also S from the superheated water table. So we can obtain the value of H. H3 equal to 3115.3 kJ per kg, and the S3, the entropy value, equal to 6.7428 kJ per kg Kelvin. So we need to determine the entropy value, because the expansion process is isentropic. So we can manipulate the value of S3 to determine the important parameter for state number 4. Okay, now for state number 4. State number 4 involves with isentropic process, where the process from state number 3 to state number 4 is the isentropic expansion process in the turbine. Okay, so we have the data in terms of pressure P4 equal to 10 kilopascal, and we have another data in terms of entropy, where S4 equal to S3 equal to 6.7428 kJ per kg Kelvin due to the isentropic process. So now we already have two data. Okay, for state number 4, we need to check the phase. The phase may be saturated mixture or maybe superheated vapor. So first we need to check. So now we have two data, pressure and also entropy. So now in terms of to check the phase, we need to get the value of SF and also SG, because for this condition we don't have the temperature value, so we cannot compare the temperature for state number 4 with the saturated temperature. So we need to use another approach, where we need to manipulate the value of S4. So now from the saturated water pressure table, at 10 kilopascal, we need to determine the value of SF and also SG. So if the value of S4 greater than SG, the phase for state number 4 will be superheated vapor phase. If the value of S4 in between SF and also SG, so the phase will be saturated mixture phase or region. Okay, so we already have the value of SF, SG, and compare. So we conclude that S4 is in between SF value and also SG value. So the phase will be saturated mixture. So now we cannot determine the value of H4 directly from the table. So we need to manipulate the equation in terms of entropy equation and also enthalpy equation that we have learned in thermodynamic 1. Okay, so rearrange the formula for entropy. So we will get the formula for the quality of steam at state number 4, where X4 equal to S4 minus SF at 10 kilopascal divided by SFG at 10 kilopascal. So the value of S4 we already obtained, where S4 equal to S3, SF at 10 kilopascal and also SFG at 10 kilopascal we can determine by using the saturated water table. Okay, substitute the value, we will get the quality of steam at state number 4, X4 equal to 0.8124, which is 81.24%. Okay, so this value represent the amount of vapor. So we have 81.24% vapor during the state number 4, and the rest will be still in liquid form. Okay, so now by implementing the what I call the enthalpy equation, so we have H4 equal to HF at 10 kilopascal plus X4 multiplied by HFG at 10 kilopascal. So HFG we can determine from the table, and X4 we already calculate, where the value is equal to 0.8124. Substitute the value, so we can obtain H4 equal to 2135.82 kilojoule per kg. Okay, for question A, we already determined all the enthalpy value, the enthalpy value for all state H1 until H4 as shown in the slide. So we know that the Q in value, the Q in equation equal to H3 minus H2. So just substitute the value of H3 and also H2 into the equation. So we will get Q in equal to 2920.45 kilojoule per kg. And the formula for Q out equal to H4 minus H1. Substitute the value of H4 and also H1. So we will get Q out equal to 1943.99 kilojoule per kg. So we know that the thermal efficiency formula equal to 1 minus Q out divided by Q in. So substitute the value of Q out and also Q in. So we will obtain the thermal efficiency value for question A, where the value of thermal efficiency for the Rankine cycle for the first case will be 0.334 or 33.4%. Okay, now for question B, so you need to determine the thermal efficiency if steam is superheated to 600 degrees Celsius instead of 350 degrees Celsius. So for this question, actually this question try to shows the example for the method number 2. Method number 2 is referred to the superheated the steam. So instead of 350, we will increase the value of T3 to 600 degrees Celsius. So redraw the schematic diagram and put the new data for the diagram, and also we need to replot the TS diagram for the new case. So now we have, instead of 350 degrees Celsius, we will have in terms of T3. So now we represent the new value of T3 with T3 prime equal to 600 degrees Celsius. Okay, the rest of data is still the same. So now you need to determine the new value of thermal efficiency for the Rankine cycle. So if you look to the TS diagram, we need to calculate the new value for state number 3, which is referred to state number 3 prime, and also new value of state number 4, which is represented by state number 4 prime in terms of enthalpy value. So we need to determine new value of H3 and also H4. Okay, the value of H1 and so H2, we can still use the same value as in question A. Okay, so now we will use the same equation of thermal efficiency. Data given, P2 equal to P3 equal to 3 megapascal, T3 equal to 600 degrees Celsius, P1 equal to P4 equal to 10 kilopascal. For state number 1, we can use the same approach as we did in as we did in question A. Okay, we will have same value of H1 and also V1. Okay, similarly for state number 2, because the state doesn't change if you compare to question A, so we will use the same approach in order to determine the value of H2 for question B. Okay, so we have P2 3 megapascal, S2 equal to S1, and the phase is compressed liquid. However, the data is not available, so we need to use the value, the equation for W pump in, V1 multiplied by P2 minus P1 equal to H2 minus H1. Rearrange the equation, you will get the same value of H2, same as the H2 value in question A. Okay, so now for state number 3, which is referred to state number 3 prime for this case, for question B, we need to determine the new value of H3, which is H3 prime. Okay, so we know P3 equal to 3 megapascal. We have new value of T3, which is 600 degrees Celsius. So if you want to check the phase, so you need to use the saturated water table based on pressure, find out the value of saturated temperature, and then compare with the value of T3, new T3 value. So confirm the phase is superheated vapor, and then use superheated water table at 3 megapascal, and also the temperature of 600. So you can determine the value of H3, new H3, and also new S3. H3 equal to 3682.3 kilojoule per kg, and S3 equal to 7.5085 kilojoule per kg Kelvin. Okay, done for state number 3. And also we need to calculate new H4, new enthalpy for state number 4. And this state actually, if you look at TS diagram, refer to state number 4 prime. So the process 3 prime to 4 prime involves expansion, isentropic expansion process in the turbine. So we know that the P4 equal to 10 kilopascal, S4 equal to S3 equal to 7.5085 kilojoule per kg Kelvin. Okay, now we need to determine the phase, check the phase for state number 4 by using saturated water table. Compare between the S4 value with SF and also SG. So still we will have S4 value between SF and also SG at 10 kilopascal. So the phase still saturated mixture. Okay, so we need to use the entropy and also enthalpy equation. First, we need to determine the quality of steam at state number 4. Substitute the value of S4, SF, SFT. So we obtain X4 equal to 0.9144 or 91.44%. So the value of X4 increased compared to the value of X4 in question A. So the quality of the steam improved by using the superheating the steam method. And then determine the new value of H4 equal to HF at 10 kilopascal plus X4 multiplied by HFG at 10 kilopascal. So substitute the value, where the value of HFG you can determine from the table of saturated water at 10 kilopascal. So the new value of H4 equal to 2379.9 kilojoule per kg. Okay, for question B, we already obtained the value of H1 and H4, where H1, H2 still we use the same in terms of data, the same data as in question A. However, we recalculate the value of H3 and also the H4 value because the condition already changed. Okay, So now we already obtained all the value of H1 until H4. Calculate Q in. So we'll get Q in equal to H3 minus H2 equal to 3487.45 kJ per kg. And Q out equal to H4 minus H1 equal to 2188.07 kJ per kg. Substitute the value of Q in, new value of Q in and so Q out into the thermal efficiency equation. So we will have new thermal efficiency equation for question B, where the value is equal to 0.373 or 37.3%. Okay, so you need to compare with the thermal efficiency that we obtained in equation B and also in the equation A. Okay, so the value of the thermal efficiency for question B is greater than the thermal efficiency of the Rankine cycle for question A. Okay, for question C, you need to recalculate thermal efficiency if the boiler pressure is raised to 50 megapascal while the turbine is maintained at 600 degrees Celsius. So now, if you compare to the question B, so the temperature of T3 fixed at 600 degrees Celsius, but now the change is the pressure of the boiler during heat addition process. So instead of before this we use 3 megapascal, so now the pressure increased to 15 megapascal. To redraw the schematic diagram, also redraw the TS diagram. So we have new constant pressure line here, where the constant pressure line refer to the new constant pressure line of 15 megapascal and fix the temperature at 600 degrees Celsius. So now we have new state that we need to calculate. We have three states that we need to recalculate the value of H. First, state number 2 that represented by state 2 prime. The second one, state number 3 that represented by state 3 double prime. And the last one, state the enthalpy for state number 4 that represented by state 4 double prime in the TS diagram. Okay, now we need you need to determine the thermal efficiency for the last case. So we use the same equation for thermal efficiency. Data given. So now P2 equal to P3 equal to 50 megapascal. T3 is 600 degrees Celsius. P1 equal to P4 equal to 10 kilopascal. Okay, for state number 1, because the data for the state number is not changed, still we can use the value of the important value for state number 1 for question A and also question B. Okay, where we have P1 equal to 10 pascal, we know that the phase saturated liquid. So from saturated water table, we can determine the value of H1 and also V1. Okay, and also we need to add one more value for S1, because maybe we can use this formula. We can use this value in order to use the compressed liquid table, because the pressure already high, greater than 5 megapascal. Okay, so S1 will be equal to 0.6490 kilojoule kg Kelvin. So the others value of H1 also V1, we can use the value that we already obtained from question A or question B. So the value is still the same because data doesn't change. Just for question C, we need to add one more data in terms of S1. Okay, now for state number 2, which is referred to state number 2 prime, the process will involve isentropic compression process from state number 1 to state number 2 prime. So now the pressure for state 2 will be higher than 50 megapascal, so we can use compressed liquid table. So P2 equal 50 megapascal, S2 equal S1 equal 0.6493 kilojoule per kg Kelvin. So the phase is compressed liquid. Use the compressed liquid table at 15 megapascal, and you need to find out the location of S2 value in the table. So the value will be in between 0.56666, 0.5666 and also 0.8234. So you need to make interpolation between entropy value and also enthalpy value, so you can get the value of H2 equal to 207.5 kJ per kg. However, for you have another option for state number 2 in order to determine the H2 value. Also, you can use the formula of W in equal to V1 multiplied by P2 minus P1 equal to H2 minus H1. But the value will be slightly different, but still acceptable. Okay, so now for state 3, which is referred to state 3 double prime. So we know that P3 equal to 15 megapascal, T3 equal to 600 degrees Celsius. Let's say you want to determine the phase, use saturated water table at 50 megapascal, determine the saturated temperature, compare with the value of T3. So the value of T3 is greater than T saturated at 50 megapascal. So the phase is superheated vapor, confirm superheated vapor. Use superheated water table at 50 megapascal and so 600 degrees Celsius. You can determine the value of H3, new H3, and also new S3. So H3 equal to 3582.3 kJ per kg, S3 equal to 6.6776 kJ per kg Kelvin. Okay, for state number 4, which is referred to state number 4 double prime, and the state involved is isentropic expansion process in the turbine from state 3 double prime to 4 double prime. So pressure equal to 10 kilopascal. Use the same method where we know that S4 equal to S3 equal to 6.6776 kJ per kg Kelvin. So now check the phase by using the saturated water table at 10 kilopascal. Compare with the value of SF and also SG in the table. So we know that S4 still in between SF and SG, so the phase will be saturated mixture. Determine the quality of the steam at state number 4, the new quality of the steam at state number 4, which is equal to X4. So the value of X4 equal to 0.8037, which is equal to 80.37%. So if you compare to question B, so the value, the quality of the steam at state number 4 for question C is decreased. The moisture content also will increase. And use the enthalpy formula to determine H4. So we'll get H4 equal to 2115.0 kJ per kg. So we already have all the enthalpy value for state number 1 and state number 4. So state number 1 in terms of H1 value, same as in question A and also question B, but we need to recalculate the value of H2, H3 and also H4. Recalculate the value of Q in. So Q in equal to 3374.8 kJ per kg. Q out equal to H4 minus H1 equal to 1923.17 kJ per kg. Substitute into the thermal efficiency equation. So we'll get the thermal efficiency equation for question C equal to 0.430 or 43%. So if you compare the value of thermal efficiency or call between A, B and C, so question C or case number 3 will have highest value of thermal efficiency, where for the question C we use the third method where we fix the value of T3 and then we increase the boiler pressure. Okay.